Hello and welcome to Statistically Significant. In this session, I will be showing how to do practicals manually using a calculator. My topic today is one-way Anova. In my previous videos, I have shown how to do Anova using MS Excel, but now I will be showing how to do the Anova and other things using just a calculator. So let us have a look at the problem at hand. We are given the data is basically on hourly productions of machines. Machines have been purchased by a factory and they want to test whether their mean speeds are different. These are the figures, the hourly outputs of each machine. So the outputs here, they are affected by just one particular factor, that is the machines. There are three different machines here, so only the machines are affecting the outputs of the products. There is no any other factor which is affecting the outputs. Only the machines, the different machines are affecting the outputs. That's why we are using just one-way Anova here. So here we are given the level of significance to be 5%. In some problems you will find it, and in other problems you might not find the level of significance to be given. You can take it as 5% or 1% as you wish. Generally I take it as 5%. So moving on to the computational procedure schemes, how to do this. See, for the students who are studying in different colleges under the University of Calcutta, while doing practicals they have to follow a certain scheme. First they need to write down the theory related to the practical problem, and then do the calculations by hand, and then write a conclusion at the end. So I will be following that scheme. Anybody can follow it, but I find this scheme to be very useful. See, the model used in one-way Anova is yij equals to mu plus alpha ij, where I equals to 1 to k and j equals to 1 to ri, and summation ri is n. That is, we have totally n observations given, where yij is the jth observation corresponding to the ith level of the factor a. So in our problem we have a factor, that's the machines, and three different levels we have, 1, 2, 3. So here our k would be 3 in our problem, and we have 5 hourly productions corresponding to each level, so we have totally 15 observations in our problem. In our problem n is 15. Mu is the general effect, alpha is the additional fixed effect due to the ith level of a, and the eij is the inherent error in the model, which are independent and identical normal 0, sigma square. Now coming to the computations. First we need to find the grand total, the sum of all the observations given to us. Then we need to find the correction factor, which is obtained by dividing the square of this grand total by the total number of observations, g squared divided by n. Then comes the raw sum of squares of all the observations given, is the RSS. The total sum of squares is TSS, obtained by subtracting the correction factor from the raw sum of squares, that is RSS minus CF. The sum of squares due to the factor A, SSA, is obtained by summation I equal to 1 to k Ti naught squared by Ni. Now how to find Ti naught squared, I will be showing you, just wait. Minus CF, so SSA is this term minus this term. Sum of squares due to error, SSE, is obtained by subtracting the sum of squares due to the factor A from the total sum of squares, that's TSS minus SSA. Now what do we want to test here? We want to test our null hypothesis is H naught alpha equals to 0 for all I against the alternative alpha is not equal to 0. Alpha equals to 0 means that there is no significant effect due to the additional factor A on the responses, and our alternative, which is alpha is not equal to 0, that it signifies that there is a significant effect on the responses due to the factor A. Now comes the Anova table. This was the variation, treatment, errors, and the total. Total is different. The degrees of freedom is the df means the degrees of freedom, the sum of squares, ss is the mean sum of squares, the f observed. Now, how do we get the df's? See, totally we have n observations, so our df for the total would be n minus 1. Totally we have k treatments here, k levels basically, I must say. There are different levels of the factor A, so our df becomes k minus 1, and the error is obtained by n minus 1 minus k minus 1, which becomes n minus k, the degrees of freedom for the error. Sum of squares due to A, sum of squares due to the error. I have shown it how to find them, the TSS. Now the mean sum of squares, it is obtained by mean sum of squares with the factor A is obtained by dividing the SSA by its df, corresponding df, SSA divided by k minus 1. The mean sum of square due to error, MSE, is obtained by dividing SSE divided by n minus k, SSE divided by n minus k. The f observed, it is obtained by MSA divided by MSE, MSA divided by MSE. Now this f observed follows the f distribution with degrees of freedom k minus 1, comma n minus k. Now why does it follow an f distribution? See, it can be shown that the sum of squares due to the factor A, it follows a chi-square with k minus 1 df, and the SSE, it follows a chi-square with n minus k df. And an f statistic is basically a ratio of two chi-square variables divided by their corresponding df's. Now, our testing rule is that we reject the null hypothesis H0 at level of significance alpha if this f observed value, this MSA by MSE, exceeds the f tabulated value f alpha k minus 1, comma n minus k. The level of significance we have taken as alpha. This value is obtained from the statistical tables. I will be showing you how to find that. Now, I must say this, when we do not reject the null, when we accept the null, then our test ends here. We don't need to go further. But when we reject the null, we have to go a step further and find why are we rejecting the null. Now, let's see how to do it. In that case, when H0 is rejected, we perform the critical difference test. First, we need to obtain a treatment means here. The treatment means are very easy to find. I will be showing you. The critical difference is given by the square root of MSE into 1 by Ri plus 1 by Ri dash. Now Ri is the number of observations corresponding to the ith level of the factor A. Here we have 5 observations corresponding to the 3 factors. Here we have 3 different machines, so we have 3 factors here. So Ri is 5, Ri dash is also 5 here. We have an equal number of observations corresponding to each of the levels of the factor A. So we don't have any problem in this case. Into this is the T statistic. Now why are we considering the T statistic here? I'll be explaining. It's a very short, it's a very easy thing. I'll be showing you why. We want to test here, our null is H01 is yi naught bar equal to yi dash naught bar. That is treatment mean for the ith level is equal to the treatment mean for the I dashth level. Against our alternative is that these two means are not equal, they are unequal. Now we check for the absolute differences. We find y1 naught bar minus y2 naught bar, the modulus of these of this difference. Then y2 naught bar minus y3 naught bar, and then we have to find k c2 such differences. See, we have k levels, so these are all pairs, so we have k c2 such differences. Now what's the testing rule here? We reject h naught 1 at the level of significance alpha if this difference exceeds this critical value, and conclude that the treatments that differ significantly. Okay, the treatment that differ significantly. Now, as I was saying, why are we taking this T statistic here? It can be shown that this yi naught bar minus yi dash naught bar, this modulus, when divided by this MSE, this whole square root MSE term, then that thing follows a T alpha by 2 with that thing follows a T distribution with n minus k ds. Okay, this is a tabulated value here. The difference, the absolute difference, yi naught bar minus yi dash naught bar divided by this square root term, it follows a T distribution with n minus k ds. Okay, now coming to the calculations part. Sorry for the camera, I just need to fix it. It's going to be a bit long video, just watch. So our data is this. This is our data. So first we need to find the grand total. We have to add up all these and we need to find the grand total. We get our grand total as 480. Then the correction factor, it's g squared divided by 15. We have totally 15 observations here. That gives us 15,360. Sorry for the camera. Now we need to find the raw sum of squares, the sum of squares of all the observations. This. These are raw sum of squares. Now we find the total sum of squares. It's RSS minus CF. It has 450. Now see, finding the sum of squares with the factor A, the formula was like this. So how do we get the Ti naught? When we add all these corresponding to the machine A1, 25 plus 30 plus 36 plus 38 plus 31, we get T1 naught. So it's basically like this. Now see, Ni there are 5 for each of the machines. 5 here, we have 5 here, we have 5 again here. CF. Now what's T1 naught? Sorry, let me adjust the camera. T1 naught, if we add all these observations corresponding to the machine A1, we get 25 plus 30 is 55 plus 91, and we get 160. And T2 naught is 31 plus 39 70, 108, 130, 185 square. It's 24 plus 30 plus 28, it's 82, 107, 135. 54, 82, and 135 minus this. We get this as so we have got our sum of squares with the factor A and full sum of squares. Now we'll finding the SSE. Very easy. It's TSS minus SSA is 450 minus 250 gets us 200. So now we'll be making the Anova table. So it's our Anova table now. We write down the sources of radiation, different sources of radiation in the model. Now we have 3 levels of the factor A, so it will be 3 minus 1, that's 2. Totally 15 observations, 15 minus 1 is 14, and 14 minus 2, that's the error DF 12. Now SSA, our SSA is 250, our SSE is 200. Total sum of squares is 450. Now the MS it's SSA by its DF 252 by 2 125 and 200 by 12 SSE by its DF it's 16 point something and 16.66. Now the F observed, it's this by this, and we get it as 7.503. Now we have to go for the statistical tables. Just wait. This is our F statistics table for the level of significance 0.5. We have given to take the level of significance to be 5%. So now we have to find F2, 12. As you can see, it follows, our F observed follows F2, 12. So we have to find at 5% level of significance. See, it's given F 0.05 with the DFs. So F2, 12 is this. It's DF1 and it's DF2, it's 3.89. So I have to write now. You could see that our F observed is greater than our F tabulated. 7.503 is indeed greater than 3.89. So we reject the null at 5% level of significance. Now, as I had said, when we reject the null, our test doesn't end there. We have to go for the critical difference test. I'll be going to it. Just wait. Now, we have got our treatment totals. The first treatment means we need to find is our first T1 naught was 160, so it's 160 divided by 5, 32. Our second treatment mean was 185, 37, and our third treatment mean was 135. That gives us 27. Now what is our critical difference here? Our critical difference is root over of MSE. The MSE value we have got it as 16.66 into 1 by Ni and 1 by Ni dash. Now alpha is 0.05. We have to take a T alpha by 2, that's 0.05 divided by 0 by 2, which gives us 0.025. So with the df n minus k, our error df, that is n minus k is the error df, that's 12 we have. Again we have to go for the statistical tables. I'll be showing it. Now in our problem we have these as 5 for all the levels, so that's not a problem. This is going to be same for every level. So now this is our table for comparing the critical differences. Again I will be using the statistical table to find this value. Now see, we have the T table here. For 0.025 with df12, our value is this 2.179. So just write it down. Now the differences and this critical difference. Now if I calculate the critical difference, it will be like this: 16.66 into, see, 1 by 5 plus 1 by 5, it gives us 2 by 5. Square root of this whole thing into 2.179. So critical difference is 5.625. It's same for all. Now the differences. This difference is 32 minus 37. The absolute is 5. 37 minus 27, it's 10. It's 27 minus 2, it's 5. So in this case, this is not exceeding this critical difference. Okay. Again, this is not exceeding the critical difference. Okay, but this is exceeding the critical difference. So what would be our conclusion here? We conclude that machines A2, A3, they differ significantly in their mean speeds while producing the output. And also remaining differences are not significant. You could see that only the difference between the machine A2 and A3, this is exceeding a little difference. That's it from hands-on practical. I hope you like this video. It's a bit long, I know, but I can't help. For more such videos, please do like, share and subscribe the channel. And for any inputs, you might write down in the comment section, and what further thing you would like to learn, you also might write down them in the comment section. Thank you.